Sir, it's done. We are ready and you can start.
Hey, good morning, good afternoon, good evening to all our friends from around the world. Welcome back to the inaugural symposia of for the American Express Lab for Data Analytics, Risk and Technology. It's my pleasure to invite you back. We had one inaugural lecture yesterday, and we have a series of 3 lectures today. We have Professor Katsikopolis from the University of Southampton, followed by Dr. Manish Gupta from American Express, and Professor Narayanan Srinivasan from IIT Kanpur as the 3 speakers today. To chair the first session, I invite Professor Ravindran, who is a professor in the Department of Computer Science at IIT Madras. He is also a Mindtree Faculty Fellow and also the head of the Robert Bosch Center for Data. What is it? Data sciences and AI.
Yeah.
And so over to you, Ravi.
Thank you, Raj. And you forgot to mention I'm also a core member of GARD. So.
Absolutely.
Okay. And it's a great pleasure to be introducing Professor Konstantinos Katsikopoulos. So Kostas, as we know him, and I were actually there at UMass at the same time. So Konstantinos is a tenured associate professor and head of research at the Department of Decision Analytics and Risk at the University of Southampton Business School. Previously, he was an associate professor and deputy director of the ABC group at the Max Planck Institute for Human Development, as well as visiting assistant professor at MIT and the Naval Postgraduate School. He works on integrating standard decision theory with the simple rules of thumb that people actually use. He has engaged with government and businesses on complex problems in economics and safety. His work has been funded by organizations such as NASA Ames Research Center and the German Science Foundation, and covered by newspapers and magazines, such as Science News. He was one of the 2 speakers in the first plenary debate at the OR Society meeting on optimizing versus satisficing. Konstantinos is a co-founder and organizer of the annual Winter School on Bounded Rationality in India at the TAPI Management Institute, chair of the OR Society's Behavioral OR Group, and serves on the editorial board of Judgment and Decision Making at Journal of Mathematical Psychology. He's the lead author of Classification in the Wild, The Science and Art of Transparent Decision Making, forthcoming by Mighty Press. Konstantinos, over to you.
Great. Thank you very much, Ravi. Let me see if I can share my content. No. See it? Yes?
Yes.
I'm guessing. Okay, great. So it's great to be here. I'm very glad to be participating in the inauguration of the DART Lab. I'm very excited about the mix of analytics and behavioral science that you're trying to pursue. I think this interdisciplinary approach is absolutely the way to go for such hard problems. Since we don't have so much time, I'm going to get immediately into my talk, and then I'll be making some connections. As Ravi said, I know a few of you, of course, Ravi also. Narayanan, he was participating and gave us some nice lectures in cognitive psychology in the summer schools for bounded rationality we're holding at TAPMI every year. And of course, Nandan, with whom we overlapped at MIT and at the Max Planck. So I'm going to present an outline of a book project that we initiated 3 years ago. It has exactly the title that you see in the screen, and as Ravi said, these are co-authors, and indeed, actually, as Ravi said, the person on the left, Ozgur Simsek, she was a fellow student of Ravi in the machine learning lab at UMass Summers, headed by Andy Barto. That's Ozgur Simsek. She's also my wife. Her student, doctoral student Marcus Bookman, is a senior data scientist at the Bank of England. And on the right is Gerd Gigeranger, who is our mentor in that kind of work. And I would say a very influential person into carrying over Herbert Simon's work. Herbert Simon, possibly one of the most important polymaths of the 20th century in the intersection of pretty much the kind of thing Dart seems to want to do. So building mathematical models, formal models for decisions in the real world, but respecting the information processing of people and by extension of machines, hence making them more usable and transparent. So in a way, I already gave you a little bit of a background of what we try to do in that book project. This is the first scholarly book by the ABC group that puts together formal work, and it's not an edited book or a handbook. So it's a shorter book, and it's a book where we try to show to people how to do stuff and evaluate them and make a connection to cognitive psychology and machine learning. You will see. But before I get to, let's say, an illustration of some of the contents of what we did in order to bring together a few decades work, let me do a little bit of preparatory work in terms of some definitions. So that will be the next 5 or 6 slides. Let me first say a little bit about this in the wild. I don't know if you heard it. It actually resonates well with the talk and the work that Greg Jamieson from Toronto was discussing yesterday. It's a classic thing in cognitive science, cognitive engineering, but not always so much followed or so much known in other disciplines. So in the lab is meant to be, let's say, an antonym to in the wild is meant to be an antonym to in the lab. So everything that approximates better the conditions under which real people and real machines have to make decisions and reason in the world as we experience it is in the wild and not in the lab where the experimenter or the modeler is trying to keep control in order to learn some things or run a control experiment and so on and so forth. I have an example here, and the example is has to do with a very English concern. So this is Bertrand Russell, of course. And the question is basically, should I go for a picnic tomorrow or not? Because it could rain. So in England, it could rain anytime. Even if it's brilliant weather, it could start raining. So that's how it works. So why am I putting that here? Of course, we all know that the world is uncertain, but we're also not that defenseless against this uncertainty. Of course, we have developed formalisms and have been refining them for hundreds of years, such as probability. That's our main device for reducing uncertainty into something manageable that we can apply calculus to. So if you consider the probability of rain, of course, we have those now. Your smartphone can give you one on an hour-by-hour basis. So we have managed seemingly to somehow reduce uncertainty into probability. Nevertheless, there's many subtleties. First of all, these probabilities keep changing. So it's a very unstable device. So your cell phone may say now that at 4 p.m. the probability of rain is 30%, but that can become 40%. Second, it's not clear at all what this 30% and 40% mean. There's many interpretations, frequently single event, and people are hopelessly confused about these interpretations. And third, and perhaps more damagingly, and now moving here to Jim Savage, who was the founder of what is broadly understood or discussed to be Bayesian subjective expected utility theory. Even Savage himself said that his theory, applying probabilistic reasoning and probabilistic calculus to planning a picnic, it actually cannot be done. The problem is too complicated, even planning a picnic. So some of the problems are one cannot imagine all the possible events, one cannot attach probabilities to them, one cannot attach utilities to them, and so on and so forth. So in theory, Savage provided the solution, but then he himself said he thought the problem of planning a picnic is in fact too wild, it's too much in the wild. So the ABC group and another number of groups that interface with us, including Nandan's group at MIT, headed by Adam Fry, we have always been trying to make do with less information, possibly in the absence of probabilistic information, which is often the case in the wild. And you'll see that this tends leading you to simpler models that are less information hungry. And the question is, are these models able to perform as well as the more complex models? And I'll get to that. Beyond that, before that, the second preparation, I'm still in the preparatory phase, if you remember. So except for the wild, I want to explain will be transparency. So by transparency, of course, it's very close to the pronounced goal of AI these days, which is sometimes called explicable, interpretable, and so on and so forth. But transparency, we specifically define it as saying something that people, these are the agents in this case, can understand, can apply, can teach to others. And I want to show it a little bit by example, and this is in a way my first case study. So this is a real data set that we're using in the book. It has to do with Pima Indian older women in the United States. They do have a high prevalence of diabetes, about 50%. Can we predict, based on some attributes, cues, features, depending on our discipline, who of these women will develop cancer, diabetes within the next 5 years? Here in this slide, you see some solutions that exist already, and they're meant to be transparent. So I am constraining myself now in terms of AI models, in those models that are trying to be transparent. So for example, Leo Breiman's classification and regression trees are one such possibility, and random forest is, as you know, a collection of all these cart trees all together. And you also have decision lists. So these three are AI's attempts, not the only attempt, but typical attempt of trying to be more transparent to people. And I'm going to be a little bit picky from the perspective of a behavioral cognitive scientist. So something I could complain about, if you look at the card, of course, it has a nice graphical structure. It asks questions. Everything that Leo Breiman was going for is here, of course. But there's some other things that can be disconcerting. For example, you have a question here, which is about the body mass index. And you see that if it's large, so if it's larger than 29.95, then you would predict diabetes for this specific person. That's fine. What could be confusing to someone who's not a data scientist is that a question on BMI comes up again with another value. And now, if you have a relatively large value, so larger than 26.35, you're not going to conclude as you did here before diabetes, but you're going to ask another question. So if you don't understand where this is coming from and that there is some kind of simple logical expressions that are different in this case, you may well be very again. Some form it stands clearly, right? One complaint here could be more one the kind of we
Sir, you are losing your voice, sir. Hello? Professor, this is the break in your voice.
I can do. Hello?
Professor, please kindly repeat that slide, Professor. Your video is frozen and there's a break in the net connection for you.
Your voice is breaking up.
So from last now.
No. Your voice is still breaking up.
How about now?
We can hear you
Yeah.
now, Kostas.
Much better. Yeah.
Yeah, well,
So, Costas,
my,
one suggestion: maybe you can keep your video turned off. That might save some bandwidth, and just share
good.
the screen.
Yeah, let me do that. Okay, so a bit confused with all these windows now. How do I get to the, oops.
We are still seeing your screen.
Yeah, I know,
You just
but
need to start. You just need to start your slideshow.
yeah, but you can also see the video, I think, which I was trying to.
I can see the video.
Yeah.
So all the way at the bottom of your
All the way at the
screen,
bottom.
you should see a button with the video crossed out.
Mm. Could it be that if you're sharing, you cannot do this?
No. It should be like a floating panel that just shows up when you bring your mouse down, like that.
So as long as the mouse comes down, the panel will come
Video
up.
options. Don't see anything actually. You can see my screen, right? So you cannot see that screen.
No, we can only see your PowerPoint.
Professor, you can stop sharing and again start.
Yeah, exactly. I think that will work. Stop my video now. I'm sure it will work now. Okay. Let's try again. Well, sorry about. Let's see now. So now, can you at least hear me, even if you cannot see me?
Yes, we can hear you clearly.
Okay, maybe that will help. So, is it true that people couldn't really follow the slides? Should I start from the beginning?
Preferably yes, Professor, because at the beginning we lost many of your
At
words.
the beginning, there started being problems. Okay, let's see how it goes this time. Okay, so what I was saying is for the prediction of whether a particular PIMA woman will develop diabetes in the next 5 years. AI, of course, has done some attempts to build transparent models, and those are either trees, as you see here, the CAR tree by Leo Breiman, classification and regression trees, random forest, which is a collection of such unpruned trees, and decision lists, which are a series of logical expressions. So I'm going to be a little bit picky now and criticize why these things are not necessarily that transparent to non-data scientists. For example, if you take the card, there's a question here about BMI, body mass index. And what happens is if the BMI is relatively large, larger than 29.95, in that case, you predict diabetes. On the other hand, this question is repeated with another threshold value, 26.35. And now, in the case of a yes answer, you don't immediately conclude diabetes, but you ask another question. So you could try to get into the point of view of a person who's not a data scientist. They could be confused why you're asking them the question on the same cue twice, why you're not asking exactly the same question, and why you're performing different actions for the same answer. For the decision list, a complaint could be that sometimes, in order to be able to understand and what the algorithm is doing, why sometimes some questions include more than one cues, as for example is here with the plasma and the BMI. So in the kinds of methods we have been developing, which is the fast and frugal tree and tallying, as two examples, there are more, we don't necessarily change too much, but we're trying to make the structure more constrained and easier to follow for someone who thinks a little more simply and doesn't have the training of a data scientist. So in a fast and frugal tree, we do have a tree, but every time we ask a question, there's always the possibility that the classification is made, as for example, for the first, the second, for all the questions, as you can see. This is a constraint. All fast and frugal trees do like that. That's why they're frugal. They don't use much information, and hence they can also be quite fast. Now, another thing that we do in the fast and frugal tree, we also force that there are no questions that involve more than one cue. Okay, for the tallying also, we simply tally the reasons. This is similar to the decision list, but again, we don't allow for two cues to be asked in the same question. So these are these ideas come from first observing human behavior and noticing that people spontaneously use such methods to make their decisions. If they use something like the tree, they're more likely to use a fast and frugal tree. And if they use something like a linear model, of which tiling is a very special case, with the weights all being equal to 1, then they they tend to use a tiling rule. Hence, the idea is that those things could be more transparent to real people, not only in the mind of data scientists. Of course, now you may say, yes, you made them simpler, fine, I can accept that. You made them more transparent, possibly. We need the empirical work for that. We have some, but not necessarily large scale. But you probably also made them less accurate. So I'm going to spend considerable time in this talk discussing that, but here's a first indication. For the problem we just saw, predicting diabetes in PIMA older women, you have the five methods here, and you have different measures. Balanced error, we just average the error due to misses and to false alarms, because there could be imbalance in the frequency of the classes. And then frugality, that we operationalize by the number of questions that are used for every classification, and transparency by the number of questions that are in every tree. Notice that those two are not exactly the same, because in some cases you stop before you reach the end of the tree or the end of the tiling rule, for example. I don't want to get too much into that, especially since we lost some time. But let me, you can quickly scan it, and you see there is a little bit of a trade-off, but maybe not as much as one thought. True, the random forest was better, but tiling was actually better than Reaper and as good as Cart. And clearly, as one may expect, the transparency, there's just simply no comparison between the fast and frugal tree scores and the scores of the other methods. Tiling is actually not so frugal because it always tends to use all of the cues. Okay, so this could mean that someone will have a reason to investigate this trade-off. It's not a given that if you make a model more transparent, you also make it less accurate. This is an empirical question. Okay, before in fact I get into this empirics and a little bit of a theory we have been developing about explaining the findings, let me quickly address something that could be in your mind. So if you have studied behavioral science and engaged in it, you have probably heard about other kinds of heuristics beyond this tiling and fast and frugal trees, and you may be curious how they relate. First, in terms of the definition of heuristics in operational research, their heuristics in computer science, this is from an operational research textbook, their heuristics don't really have to do much with people. People are consuming them as decision makers, possibly, but they're not producing them. So heuristics are simple computational shortcuts that allow to find a feasible solution. That's also a good thing. You don't always go for an optimal solution. In some problems, just finding a feasible solution is good. So that was a little bit of one of the original meanings of heuristics. And in behavioral science, Tversky and Kahneman have been extremely influential into proposing another meaning, which brings, of course, the people in the forefront. The people are now the producers of heuristics. And where before heuristic was associated with the word good, so to say, now it's associated possibly with the word of error, as you see in this definition. Of course, Tversky and Kahneman were careful and they said sometimes heuristics are good, sometimes heuristics are bad. But the writing was such, as in this definition, that emphasized the errors. The definition that we are using in this work, and I would like somehow to put on the table, I think it's rapidly gaining ground in behavioral science and sometimes even more outside behavioral science, in more practical disciplines, is that heuristics, of course, are models of what people do. They are quantitative. They're not verbal labels as in the Tversky and Kahneman work most of the time, or at least in their original work. They're models, so possibly more amenable to formal analysis as we do here. And part of this definition also includes an attempt to say that sometimes they lead to good outcomes and sometimes they lead to worse outcomes. So before getting a little bit more into the meat of what we did, I wanted to place it in the broader context of behavioral science. I think that's important. As the DART lab is trying to make contributions that spawn and interact productively with other areas such as behavioral economics and cognitive psychology, possibly even law or business, I think it's important to know that there is many ideas about what a heuristic is, and you could even possibly develop your own idea, and this can give different insights than the traditional insight that a heuristic is something that people do because they cannot do otherwise, and this leads to worse decision, which if you look at Herbert Simon's writings, you will probably strive to find him saying that. He said so many things. You may find something like that, but he definitely emphasized that heuristics are, in some sense, the only reasonable solution to making good decisions. But let's unpack a bit what we did. Let me formalize, so to say, a little bit of a claim. It's not very different from what I've been saying, so we can go through it maybe a little bit quickly. We are trying to contribute to the literature in cognitive psychology, operational research, which is in a way the core of analytics, as we all know, as well as machine learning, and try to say that not in the lab, not if you data fit or not if you choose the problems, but if you look at the representative ecology of problems, then possibly simplicity and transparency are not necessarily a trade-off with accuracy, and we have to understand when we can have our cake and eat it too, as they say, and when we cannot. Um, now, because now I cannot even look at the clock. Can somebody tell me how much more time we have so I don't eat from other speakers' time and from questions' time?
About another 15 minutes,
Okay,
including
I think
questions, including the questions.
that's including the questions. So I'll try to
Yeah.
be done in 10, so maybe even earlier. So we have a nice conversation that could be more useful. So as you see, last bullet of the slide, I have a few cases. You already saw one with the PIMA women, but I have some more salient ones. And then to tell you a little bit how we're building the mathematical theory. I was anyway not sure I would go into the mathematics, but I think I'll just outline. So of course, this is the White House. And as you may be guessing, I'm going to be talking about the previous election. So Nate Silver, very successful in many occasions, unsuccessful here in terms of putting more than a 50% probability, considerably more for Hillary Clinton while Donald Trump won. So he was inaccurate. Of course, models cannot always be correct. We know that already from George Box. The idea is that whether they're useful. Silver is attempting to be useful and transparent in his website. So if you click through various links, you will find an explanation of how he came up with the 71% probability prediction. Again, I would ask you to think not like data scientists. I know it's hard for people like us, but we have to. If we're going to be reaching out to consumers and policymakers and other decision makers, we have to think like they think. So I'm not going to go through that, but basically what it kind of says is that his model is a regression on outputs of regressions, basically with corrections, with technical adjustments, trying to avoid overfitting, and so on and so forth. And I just don't think that clears the bar of being transparent to a normal, quote unquote, person. Another way is to do it based on a domain theory that includes psychology, sociology, economics, people, and framed in plain language that people can understand. So a political science professor from Washington, D.C., Alan Lichtman, has done that. He has come up with essentially a Turing rule. He has 13 keys, which are cues, features, And he has a tallying rule which says if 6 or more of those are false, the challenger will win. They're all phrased so that they are true or false. Some of them are a matter of reality, a fact. For example, key number 3, the incumbent party candidate is the sitting president, either he is or she is or not. Others require some kind of judgment, as for example, no sustained social unrest during the term, blah, 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 and so on. Nevertheless, what Lichtman always does, he fixes those cues, he makes the judgment a few months before the election, and then he lets it go. In the case of Hillary versus Donald Trump, he had predicted Trump will win by finding that 6 of these keys were false. For the record, because that's probably coming as a question, he's now predicting, he has fixed his model now already, he's predicting Biden. Okay. On to a little more complicated situation where it's a little more clear. By the way, I think you've been seeing it, that as we're moving from the PIMA women to the election and to this example now, you can see that probabilities look more and more scarce to find, and this is really the case here. So this is something I worked on personally with a doctoral student, and what he did, he went to WikiLeaks at the time that it was still possible to get stuff from WikiLeaks. That was only for a week, and he was able to download 1,060 reports from NATO checkpoints in Afghanistan for 6 years. There are 7 successful, quote-unquote, suicide attacks. The big problem here is that many times civilians try to drive through these checkpoints, and what happens is they get nervous, they don't stop on time, or they think they could just go through, and then they're being shot eventually by the soldiers, resulting to injury or death. Everybody agrees, no matter if you're in the right or in the left part of the political spectrum, if you're not in the spectrum at all, if you're neutral, if you're an activist, if you're a military person or whoever you are, everybody agrees that these kinds of casualties are too many. So can we reduce them? This is the data that Nicholas, the student in Berlin, downloaded. This is the way report looks. There's access here for sensitive information, but you see you can find cues, features, attributes from this kind of data. For example, this car had 2 local nationals. It failed to stop, so both of the people were wounded. So we know the cues and we know the outcome. So we can build models. The problem is, I said, that we don't have any hits. If by hit you mean that the soldiers were able to stop a suicide attack. And we have very few misses. So you cannot really build reliably any of the models like CART. You cannot build anything. And here comes another possible advantage of the simple heuristics, such as the fast and frugal trees we're developing. They can be induced statistically, just like CART. And in the project, we spell all these different rules out. This was, to the largest extent, the work by Osgur and Marcus to specify formally these rules and to test them and to pick the best ones and to show how they do compare to other rules for inducing trees, such as in CART, to also check how often CARTs are fast and frugal trees and so on and so forth. But beyond this statistical world, the fast and frugal trees are robust, let's say, to bad information, impoverished information in the wild, in the sense that can also be used by standard methods of human factors, such as cognitive analysis. I'm going to skip that in the interest of time. This simply, currently, soldiers don't have any formal, precise method, but just some vague instruction, and we provided, which is in plain English, and we provide again some instruction in plain English, but which is formal and can be replicated and tested in a simulation. So this is again a fast and frugal tree, 1 question, possibility of an exit, only 1 cue. And it was devised by sitting down with practitioners without them looking at the data, because that would be equivalent to data fitting, but simply inducing the tree non-statistically, which we're able to do, and it wasn't able to do for any other methods. Quickly, this is a very good cue. If there's more than one person in the vehicle, then almost certainly this doesn't include hostiles, suicide attackers. Everybody agreed with that, so we put that on the top of the tree. And then we went down with a few other intuitive cues mentioned in the interviews. And if had this been used, then we would have reduced civilian casualties by more than 60%. And in fact, because this never happened, this is just an estimate. And it is in a way an upper bound, because this 78 includes that everybody that was classified as suicide attacker was hurt. But in fact, in reality, soldiers were more subtle in applying force, so they were not hurting anyone that they thought was a suicide attacker. But anyway, finally, my last case, and I want to flag that as well, because in the previous example, for example, with the PIMA women for the diabetes, we engaged in normal cross-validation out of sample. Here we're engaging in out-of-population measurement, in the sense that really, here in this case, where the idea was to predict cancer survival times for people, all models were trained in one population, literally in one country, but they were tested on other countries. So if you look at this paper in bioinformatics, there were 7 or 8 countries, I think, and you were always testing on countries that the model had not seen. So this is a tough, real out-of-population test. And as you can see here in the parentheses, you have confidence intervals. These are, again, balanced errors. If you quickly scan it, you will see that basically tiling, this very, very simple thing of just getting the cues and adding them, but just only estimating their cue direction, the future direction, you do as well as good benchmarks in regularized regression, such as RIDGE and Lasso. Okay. I had forgotten that I have the simple, an even more striking case, but I think you may have seen that. And we also have a journal article coming out. I'm just going to skip through it very quickly. It really has to do with the Google flu trends. By many people, it has been beaten to death. I'm skipping now. Sorry about that, but I want to tell you a little bit about the theory. It's also in the book and a journal article. Quickly, if you look at only that, you see, if you're trying to predict the flu, the Google flu trends, the red curve, is very bad. And if you simply do either a two parameter linear regression on the most recent observation, or only use that observation without using a regression, which is called naive forecasting. And here's the blue line, the heuristic. You do much, much better, actually. So we thought that was striking and surprising, and building on the results by Leisure et al. in a very strong way. Okay, we also have, of course, meta-analysis. It's in the book. We have not just this, we're not cherry picking. Here you can see a little bit of the larger picture. It's not very different if you use something like random forest, but we're picking the transparent AI method, CART. And you can basically see that, in fact, here there's a slight advantage to CART on the average, but not for every data set. Each point here refers to a data set. And clearly there's a big advantage for tiling and fast and frugal tree in terms of transparency. Okay, luckily I don't think I need to spend too much on that. The bias variance decomposition in this crowd, I'm sure a lot of people know it. Of course, strictly speaking, the bias variance decomposition applies to a regression problem, not to a classification problem as we have here. But the story has been unfolding in terms of the regression problem and the theory. You know that the prediction error is basically a trade-off between bias and variance. And the idea often is that simple models, of course, have more bias, but they have more variance. What we have been having, this is a high-level summary of the analytical results, is that, of course, this is well known about the statistics, that bad information, no probabilities, information in the wild can lead to lower variance, but also structural reasons can lead to simple heuristics such as lexicographic heuristics, as fast and frugal trees or tiling, in fact, having sometimes optimal bias, or at least bias equal to standard linear models. Dominance is a of conditions that leads to that. There's been good papers published on that. I'm not going to go to that in case someone really wants to. I want you to see that it is here. Under a quite wide range of dominance conditions, which are not impressive. This is also Osgur's work at NIPS, which are not rare in the real world, these kinds of dominance conditions. In fact, you can get the simple heuristics to, in fact, have optimal bias. So that was also something people didn't really expect and gives a theoretical background. It's not simply getting lucky and finding that transparent models are quite accurate. Okay, let me wrap up. Since of time, this is coming up, as I said, and I will leave you with this on the screen, which is the claim. The claim was that we set out to flesh out and formalize what Herbert Simon had been saying for decades. We tried to connect to models, not only concepts or verbal labels across psychology, OR, and machine learning. And basically, we wanted to understand a little bit better this purported trade-off between transparency and accuracy. Leaders in interpretable AI, such as Cynthia Rudin, have also been vocal in saying that this need not be. And, we're trying to contribute that. And I think as Dart is making an entry into solving difficult problems in an innovative way, there's no question that IIT Madras has an excellent capacity into building the algorithms. I simply wanted to just try to plant the seed, as Nandan and knows from his various visits to the Max Planck and my visit at MIT, that it's possible to perhaps build some algorithms by having one leg onto human psychology, and perhaps make them at the same time as accurate as before, perhaps even more sometimes, and transparent. So thank you for listening. I'm sorry you cannot see me. I'm open to questions now. We can also get rid of the slide and put back the video. I don't know what's the best way, so we can have a nice conversation now.
Yeah, I think you can try starting a video now. So hopefully,
okay.
Once
Should I sharing? Right, that would probably be better.
Sure. Yeah.
Yeah.
So
okay.
Folks, field is open for questions.
Let me. All right. Good.
So, Ravi,
I have a question. I'm Rahul.
Yeah. Hi, go on.
The heuristics that you were highlighting in the claim, are you talking about domain-specific heuristics or in general domain-agnostic heuristics?
That's an excellent question. Of course, to the extent that we get inspiration by behavior, in every domain, the heuristic may look a little bit different. So, for example, the one that you saw about the checkpoints of course, in which you will have the exact same thing. But the formal aspects, they're domain general. We emphasize that. In that sense, we're on the same footing and level of rigor with any other data science or our economics approach, which tries to build general models. It's simply that the structures we emphasize, I didn't go through that, but if we look at the tree structure, for example, it's always a lexicographic tree structure, right? With this exit at its level. For the linear model, we'll simply look at unweighted combinations. So they're both domain specific and domain general in these two senses.
Okay, thank you.
Yeah, Raj.
Roger.
Kostas, thank you very much for a very insightful talk. I had a question regarding what one can assume in terms of the expertise level of the user. So the analogy I have in mind is Atul Katwandi and others have written about checklists, and they say that when you're trying to design a checklist, you make something very simple. If it is really for the expert, because you just need to jog his memory, whereas if it is meant for a novice, then a very detailed one. Is there something along those lines that one needs to take care of when designing?
This is also, I think, this would be very important for building some good application that American Express or your other sponsors or whoever you're working with will be happy. So of course, in what we do with the checkpoints, the experts are the users, the soldiers, you can have it a little more complicated, if you will. It's not going to go to the public domain. If you're talking now about these other kinds of applications that lately have caught the public eye, such as being rejected for a loan, being tried while you're awaiting bail, where the demands of transparency are and should be enormous, of course, you have to put the bar much lower. Here, what I would say, there's a sense in which for many decisions that we're all making, we're all experts, right? And we all know a lot. So if I'm going to use if I'm going to pick up an apartment or a car, I've done this or I've done similar things before. So I don't think it would be wrong or a big burden to ask any regular consumer to sit down with you and make some trees and then test those and so on and so forth. It's again, as with Rahul's question, this has two components. It has a component of domain specificity, and it has a component of domain generality. Of course, sometimes I think our approach will fail, as all approaches fail. The question always is in building the toolbox and knowing when to go the information hungry way and when you can afford not to. Yeah. And I guess our message, because this is really, I'm really just a messenger of a research group that's growing and growing, has been working for decades and in different universities. The idea is to really try to understand when to do one and when to do the other and not assume. Many people are assuming, oh, if you make it simpler, it's going to be worse. Maybe you want to make it simpler because you have to, because people have to understand why they didn't get a loan, but it will be less accurate. I think, if we are scientists, we simply have to test this empirically. It's not just because it looks like it. It has to be, or that it is like that in all cases.
Great.
So this is really interesting for us also. One of my PhD students has been doing some work in this direction. Essentially, we want to learn simple models, right? And what we do is we change the data distribution so that the model fits better to the new distribution. But the question is it should perform better on the test distribution. So the training is different from the test. And we're able to get much, much better performance. Sometimes even like 150% improvement on the test data. I'll send you some of those papers.
Yeah,
I'm
I
really
would like
encouraged
to
of
see
this.
that. I think actually these ideas are in many different places. Simply, I think still the balance of opinion, which also influences research, is in saying if you make it too simple, it cannot be good. It's a similar balance of opinion that's to some extent unfounded, exists in the behavioral science. If you let people decide, they will be bad, But this is really not always true. There's still things in which machine algorithms cannot make as good decisions. Maybe one day everything will be automated. I don't have a problem with that, as Greg was saying yesterday. But we shouldn't think we're in that place if we're not yet. That's all, right? And we should get in that place with measured steps and knowing what we're doing before automating everything.
I completely agree.
Yeah.
So
Good,
if
good.
Thank you very much.
Guys. Very nice to see all of you. I'll switch my video, but I'll stay around, of course.
Thank you.
Thank you.
And I'm dropping off.
Okay.
Bye.
Thanks, Avi, for chairing the session. Now it's my pleasure to invite our next session chair, Professor Rahul Marathe, who is with the Department of Management Sciences. Rahul, over to you.
Yeah, very happy to introduce the next speaker, Dr. Manish Gupta. He has been featured in the top 10 data scientists in India. He's currently Vice President with the American Express. where he leads machine learning and data science team that builds state-of-art machine learning solutions and leverages them in risk and analytics engines across the world. He's also the head of on credit and fraud risk center of excellence at Bangalore. Manish has extensive experience in successfully leading enterprise-wide AI, machine learning, data science practices across various industries such as internet, e-commerce, banking, BPO, defense. He has served the country as a scientist with DRDO. He holds a PhD from IIT Delhi in the area of machine learning. He has published several papers, has US patent, has multiple citations. So very glad to have Manish today with us. Looking forward to the talk. Over to you, sir.
Okay, thanks, Professor Rahul. I think it's a really nice introduction. So let me share my screen to share the content of it. Okay, I hope you can see my screen.
Yes, we can.
Okay, first of all, welcome to all of you to have this inaugural lecture on the analytics at MX. So here, actually, I would just like to mention the kind of analytics, the kind of machine learning, the kind of use cases we solve. I try to have it in a more like a very use case oriented kind of talk, so that the audience can understand the kind of use cases that we work with. So let me start with. I think I just would like to start with about American Express. This slide is not about kind of sales pitch. It's more about to make you understand the complexity involved here with respect to decision making that we have in terms of the data, in terms of the money involved into this. So American Express obviously is the global brand which has more than 100 million card in force. At the same time, there are around more than $1.24 trillion of worldwide bill business, which means that amount of worth of transactions go through our systems. At the same time, we have around $43.6 billion of revenue, and we also have a worldwide presence with around 64,000 employee base. So you could think of it the kind of the card members, the kind of geography we work with, the kind of the business, the kind of dollar value we work with it. So in that case, the having the decisions which are more analytical and data driven is very critical for us. And we also having a center of global innovation, we call it as that, because we have an industry best fraud and credit risk decision science teams, as well as the models in place. In fact, most of our decisioning are data driven and machine learning based. We also have a next generation of advanced marketing analytics and capabilities, which make us more personalized solutions and offering for our card members and improving their customer experience. We also have set up the first financial services. We are the actually first financial services company to set up an AI labs way back around 10 years back. We also have analytical consulting for business partners across the globe. So you could think of it the kind of problem that we work, and that is also across various use cases. Before I jump into the use cases, I just like to highlight the kind of the data advantage that American Express is having it. We have a millions of buyers, at the same time millions of sellers. You could think of it, they produce billions of transactions annually, and those transactions may produce trillions of combinations. So having such kind of a large voluminous data has a lot of information to for us to really understand the customer trends as well as their patterns. And obviously, we use only permissible use of the data, because we are highly regulated industry and we can only use the data as per what is regulations are let us to do. At the same time, most of our decisioning and uses of the data primarily focus towards to improving the customer experience. I would also like to mention about the advantage that American Express is having it in terms of we call it as a AXP Global Integrated Network advantage. You could think of it. It's a many times you might have heard that the many credit card companies or credit cards which you have seen, they are, let's take an example of ICICI might be the issuer, but the merchant being acquired by somebody else, then they might be using some networks like Visa or MasterCard kind of networks. So essentially, there are multiple partners involved into this, and the data might be reside at a different partners at a different granularity level. But being an MX, we not only issue the cards, but at the same time we also acquire the merchants and we own the networks. So we basically provide us a lot of holistic view about the merchant data, the transactional data, at the same time the card member data. Plus, we also externally source a lot of data. What we do with this data, we obviously make use of this data to more personalized servicing, better target marketing, at the same time better risk management. These are the few use cases we are having it, and that provide us this network advantage that we have, provide us a 360-degree view of the data of the customer, and that help us to serve them better. I also would like to mention about the how we drive strategies across customer life cycles. You could think of it, there are multiple ways that the customer life cycle is span. Like targeting is more like kind of acquisition stage. We target the relevant customer base. At the same time, we do underwriting, like who are eligible to have a card, basis their needs, what kind of a limit that can help them better manage their exposure. We also understand their spending patterns so that we could offer them a loyalty and reward programs. We also understand their financial needs, and so that we could able to drive the engagement in their spending accordingly. Similarly, we also understand some of the key other. We also predict some of the key customer trends with a high degree of accuracy, and obviously uh, this only for the customer experience improving. That's what we do. Let me move on to the without further delay. Let me move into one of the use cases. How do we identify a customer credit worthiness using the payment information? I just would like to give a highlight about how the payment information looks like, what kind of information we extract out of it, how the data looks like, and how do we identifying the customer credit worthiness using the payment information. Let me start uh, with some of the payment landscape that we have. We actually have a lot of payment informations from the internal as well as external side of it. We also understand the other payment informations values, like we also understand the supplier payments. We also have the informations about the bounce payment informations. We also understand the payment channels from various like auto payment, transfer, all those kind of channels. And if you look at that this payment informations, we received more than 50 millions of payment transactions in a year, and that too also from 20 different markets and countries. We also have a time series view of this information so that we could understand those payment behavior of those card members and our commercial enterprises whom we support. And just to give you an examples, like and that payment channels could be very different for a different market and different customer base. For example, from a Japan side of it, most of the payment channel is auto payment, like people okay to have a auto debit kind of a payment channels, whereas the markets like US and US and India, they are very different in that case. To think about there are multiple the dimensions of the payment, there are different geography involved, the volume involved, not only volume but longitudinalness also involved into this payment landscape side of it. Let me also start with the examples just to highlight how these informations can be used, or with some example. Let's say there are two customers. One customer A, which on the left hand side, you could see that the customer is paying every day, every month their min due. Let's say min due is the minimum payment the customer is supposed to pay every month out of the total balance that the customer have. And if the customer pay that amount, we consider that customer as current. If they are not able to pay us, we consider them as delinquent. Uh, in the left hand side, you could see that the customer A is paying month on month the min due, which is almost similar to that min due, but he's paying before in time, like he's paying every month on time, but paying only min due. Whereas the customers, uh, whereas the customer B, you could say that he's paying the entire amount. Let's say in July, he's paying 2,000, whatever the balance is that. Similarly, on the other side of it, and so on. Uh, but sometimes he also missed some of the payments, and you could think of it. The customer B might be a traveler. He might have missed some of the payments for some days, but he can come back. Then the question for us is that who is more risky versus the other? You could say that those who has missed some of the times might be more riskier, but historical data says that those who are having paying only min due are more riskier because their chances that if they are further financial stress on those customers, their chances that they may go delinquent because they are only able to pay their min dues. So that kind of riskiness we are able to capture it from a more time series way. If so you could think of it, how do we extract these features from such complex data? Although in the previous example, you just see a very simple examples, min due versus non-min due pairs, and min due is generally more riskier as compared to the one who just misses being a traveler or some of the days. So you could think of it, we have a time series view of the data, we have the lot of breadth of the payment information, at the same time, there are a lot of markets involved. So there's definitely a requirement for such a feature engineering tools. In fact, we leverage something like RNN kind of a networks to mine those kind of time series data in a more efficient way. We do a lot of feature engineering, and those features finally goes into our models, machine learning models to make use of it. So the payment is just one piece of the entire puzzle. If you could think of it, we at an MX solve several such key business problems, like not only just payment, we actually make more than 50 different predictions across the different customer life cycle, and there are multiple, like more than hundreds of, like in fact 250 data scientists that we have in the American X space, who actually the brilliant minds in this space, and actually who solve those kind of problems. The problems could be whether this incoming transaction is a fraudulent transaction, yes or no. We also so what should be the line of an approved applications, we also decide on that side of it. We also decide will the institution or individuals will become a default or a bankrupt. We also decide on whether we should approve an application or not. So the multiple of those decisions, I just mentioned, there are more than 50 different decisions that we take, and the underlying data that goes into this is, I just mentioned about the payment, but there are multiple such data sources that we leverage from a different perspective. Like we have a huge span data, just to give an idea about that. Even for a single market like US, we have more than 20 million customer base, and they produce more than 400 millions of transactions in a month, and that too also like billions of transactions in a year. And those transactions has multiple, as I mentioned, the trillions of combinations to work with. We try to leverage those informations. We have the lot of bureau informations. We also leverage the demographics. We also understand the financial statements. We also understand some of the ratings for the commercial businesses. We also use the commercial bureau. So we actually, for those decisions, that kind of data, we use those machine learning algorithms like XGBoost, KNN, a lot of deep learning, and this data is not a simple data. It's a petabytes of the data, and that 10,000 such features we create out of such data in order to make our decisions more precise, so that we could able to serve our customer in a more precise way and help them and improve and help to have their better experience at MX. I just would like to also mention another use case where how we use deep learning techniques for real-time fraud prevention. As you might have seen that there are a lot of buzz around the deep learning side of it, but most of the solutions that or the application exists for deep learning are unstructured data side of it, like images, speech, text, and all. There are not too many successes in terms of uh, structured data like the we have, especially the financial institution have it. So we actually leverage some of those solutions in a real-time framework because the fraud has to be detected in a real time, and and we have used this one. I'll just give you some glimpse around that. Before getting into this, I just would like to mention about the fraud detection side of it. In fact, we call it as a fraud prevention because we are proactively preventing the frauds, not just as a reactive manner detecting the frauds. So we identify and stop fraudulent transactions as early as possible. We avoid disruptions of the legitimate transaction because that may hurt the customer experience. That's why we have to have our system in such a place so that we should not disrupt any legitimate transactions. We also strive to meet our customers' growing expectation as well as trust along with security. And obviously, the preventing fraud is directly related to the increase in revenue for us. And as I mentioned in the beginning, that we have more than $1 trillion of worth of transactions goes every year in the form of a charge volume build business, and we have only just few thousands of transactions as being fraudulent. So we have to be very accurate in our fraud detection side of it. And fraud is not a simple problem, as I mentioned, because the customer experience is the key here, because whatever we take any actions, we don't want it to hurt our customer experience. That is the I think that is the principle that we live in as a company. We need to have our customer experience as the supreme, and at the same time there are multiple type of frauds can happen in terms of online frauds. It can be account takeover, it could be even at application stage, it can be whether the card might not have received, it might be stolen, it could be counterfeit. So there are multiple type of frauds might happen, but at the whatever we do, we need to uh, uh, also take into account what is the customer experience, whatever solution we bring into the table. I just would like to mention that this is the recent innovation that we did for a real-time fraud prevention by using the recurrent neural network. In fact, we created a RNN intelligence to detect sudden change in short-term spending trend. Let me share my video. I think it's a simple video. I just would like to see whether you could able to hear it or not.
There is no voice.
Okay. So I think maybe I need to share it in a different way. Just give me a second. I stop sharing and share it again. Sorry, I think
Sure.
I might have I might have shared in a different way. Okay. Okay. I hope now.
Gina is a loyal Amex customer, so she uses her American
Yes.
Express Gold Card for her everyday purchases. Our fraud team checks her RNN score using innovative technology such as deep learning techniques to identify potential fraud earlier, faster, and more accurately. When Gina's score stays low, we approve each transaction with our system learning more every time. One day, a fraudster steals Gina's card and heads for a shopping spree at a high-end fashion store. Our big data analytics notice the suspicious change in spending habits, and with a high RNN score, the card is declined. We reach out to Gina to verify the transaction and realize her card's been compromised. The card is canceled, and Gina's money stays safe, and the fraud is prevented.
Okay. I hope this video might have given you the kind of a experience that the kind how we use those that kind of technology, especially the complex networks like RNN, to improve the customer experience at the same time saving dollar for us. And I'm not getting into the details of this particular use case because that requires a bit more time. I just wanted to give a highlight of it. In fact, we are showcasing this use case in a NVIDIA GTC conference, like GPU Technology Conference, which is a flagship conference of NVIDIA in the October. And think about to enable this kind of solutions, we need to have the real-time inferencing, which can work in a few millions milliseconds side of it, and that could able to also have such kind of volumes of transactions to work with. So we actually partner with NVIDIA on that side of it. Now we have a GPU accelerations for a real-time inferencing for this solution, and we have deployed the solutions in production.
Gina.
Okay, so let me bring some more flavor of the use cases. We also understanding customer interactions for a better business insight. So we not only have risk use cases. There is a separate team which we call it as the enterprise digital analytics. They also have a very strong data science and machine learning team at as well as analytics team at their end, and they also leverage the data a lot for various use cases for betterment of the customer experience. I also have one more video just to show you how this information may get leveraged for having again a personalized experience to the customer at the same time or better serving them. Let me play one more video.
How do we delight customers while growing revenue? Data analytics help us deliver personalized offers. It's the 1st of January. Gina joins the gym, signing up with her Amex card. Our personalization engine gets to work. It looks at spending behavior, demographics, and more, analyzing one of the world's largest and most valuable data sets. This gives a complete view of Gina's lifestyle and preferences based on her spending patterns. It uses constantly evolving self-learning algorithms to test offer strategies. We send Gina an offer, a new Amex product, or a merchant deal. If Gina's getting fit, which offer will appeal to her more? We send her the most relevant offer, the 15% off on the latest sports shoes, making Gina happy. Our algorithms continually review several billion transactions annually by Amex customers, worth over $1 trillion across 130 markets. Our algorithms are always improving, using our global integrated network advantage, which makes offers more relevant, timely, and delivered through the best channels.
Okay, I hope this use case also mentioned about how we leverage such amount of the data for personalized best offer to the customer. I just would like to highlight a few more just to explain this use case in a better way. So just to give you some idea about how we gather customer interactions across their life cycles and how do we make money out of it. Like customers come on board, so we may have some kind of annual fees associated with that. Customer also transact at merchants. We also incur some kind of discount revenue out of it, which is kind of X percentage of a transaction amount. The customer pays partial bills, then we also get the interest on the leftover balance on this one. And customer also opt out for a systematic payment plan for some of their high spending. So we basically fix the monthly charge that we do for such kind of a payment plan. The customer also finances a loan that we get an interest on those loan. And obviously, we would like to have a better loyalty customer service side of it to increase loyalty as well as engagement. So think about all those touch points are producing a lot of data and a lot of business for us, and all those things are going into our machine learning engines I just talked about. Just to give you some more flavor towards to that, let's say how I just wanted to highlight one of the analytics behind offering of a systematic payment plan. You could think of it, we use something called KNN-based machine learning algorithms. This is the card member data running every day for millions of card members. So we understand what is the similar needs, similar kind of customers that we have it. And our analytics basically recommends the type of EMI someone would like to have it for their high spend in a more systematic payment plan that we call it, and highlight the most recommended one for the higher uptake. And we not only have this one, we basically use those informations and the machine learning models automatically, which recommend the loan duration also, what kind of a best loan duration customer we should offer to. And that basically help us to also understand this one. Not only that, we also know that how to optimally place those banners as well as the style so that of the confirm button to drive the higher engagement. Think about it's not only about personalizations, but at the same time applying the machine learning in terms of understanding the long durations, but at the same time also having some the personalization with respect to the style so that we can engage the we can drive the higher engagement. So this is one of the use cases I just wanted to bring it out. A few use cases that which has help us to see that the kind of use cases, the kind of data that we have. So this is kind of last slide I have. From my end, I am happy to take any questions that is there.
Well, thanks a lot for the awesome introduction on really complex data sets. Yeah, the floor is open to questions now. You can stop sharing the slides,
Yeah.
Manish.
Okay. Thank you.
Manish, thank you again very much for a very interesting talk. I had a question about how these kinds of models get deployed. So I presume, given the volume that you're talking about, these models kind of run in real time, or do you have challenges in performance that are required from the real time, which therefore places constraints on the nature of the models that you can use?
Sure. I think that's a very interesting question. In fact, we have a very high infrastructure at our end in order to deploy. First of all, these models should be real time. Like, for example, you can't really hold a transaction and flag them later on as fraud transaction. It has to have a real time. It can't be not even near real time. It has to take within the millisecond that decision. That is one. So the real time aspect is there. With respect to our deployment, I just mentioned about that. Even for the recent use case of RNN, we are leveraging the GPU technology with the TensorRT kind of frameworks, which enable us to meet those SLAs. And we mostly have a real-time sequential inferencing at our stage, and that enable us. We also have some of the high-end mainframe systems also, which also help us to have those kind of transactions speed. So all those machine learning models are essentially deployed in a real-time framework, and because of the infrastructure, because of the talent, because of the in-house solution that we built or innovation that we did, I think we are able to deploy most of the solutions. Although there could be some solutions which could be offline, that system also we support, because not all these decision making or all the models requires to be real time, and there are certain models that also there in the offline mode as well, but with a fixed frequency. The personalization engine, all I just mentioned, I think they are also sort of a real time update. In fact, we have a things called self learning models also in place, where every day the models kind of get refreshed also, in order to understand, or in fact every week I would rather say that, in order to understand the recent trends of those fraudulent events, and that also get feed into the system. So I think there are a lot of sophistication goes into the system. In fact, I'm happy to say that our fraud rates are kind of, or write-off rate are essentially one third of the industry. So we are best because of the team, because of the data, and because of the capability that we are able to build.
Wow. Manish, I have a question.
Okay.
All the you mentioned that you serve more than 130 markets, and each market or each geography, each nation has different regulatory requirements. So, given the different data privacy laws that you have to comply with, how much of data merging can actually happen?
Yeah, sure. I think that's a very relevant question. And as I mentioned in the beginning also, we are highly regulated industry and we abide by all the local laws, or the laws of the land which are prevalent in its respective market. So obviously, we under whatever the permissible use of the data, only that we can leverage it, and beyond that we are not able to merge the data, and we have the compliance team, internal clients compliance team, fair lending team, which help us in terms of what can be permissible use or not. So I think you're right. certain regulations, we are definitely not using it, some of the data points, but obviously wherever it is a permissible use or for the help of for improving the customer experience, we do that. So I think that's what I can answer.
Okay. I mean, one more follow-up question, if you allow me.
Sure.
This regulatory requirements may also put a constraint on computational capability, right? I mean, if some country says that the hardware should be located only within that country, so all the algorithms have to run only on those machines. So there is one more dimension of that complexity.
Yes, I think you are absolutely right. The data has to be reside. There are certain company regulation like the APR and all, which basically not let the data to go outside the country. So I think that's why we might have various versions with respect to the different market that works for a need of that market. And obviously, like that's how I think we operate. And as I mentioned, like that is a challenge, but that challenge we take into in a more positive way and to abide by the law.
Thank you. Thank you. Any more questions? Okay, so let me thank Manish for really insightful journey through the financial analytics. So thanks a lot, Manish. Thank you.
Thank you. Thanks for giving me opportunity. Thanks for
Our pleasure to host you.
Okay, thank you.
Thank you. Professor Raj, over to you.
Thank you, Rahul. And for the last and certainly one of the most awaited talks, let me invite Professor Lata from the Department of Management Science to chair the next session. Lata, over to you.
Thanks, Professor Raj. Good evening to all of you present here. It's my pleasure to introduce Dr. Narayanan Srinivasan today. Dr. Narayanan is presently professor at Interdisciplinary Program in Cognitive Science, IIT Kanpur. He's been working at Center of Behavioral and Cognitive Sciences, University of Allahabad for last 16 years. He studies mental processes, namely attention, emotions, consciousness, and very popular decision-making across multiple methodologies which he uses. Dr. Srinivasan is a fellow of Association for Psychological Science, National Academy of Psychology, India, and Psychonomic Society. Today, he is with us to talk about capacity, magnitude, and control effects in decision-making. Post your talk, Dr. Narayanan, we can have a couple of minutes at least for Q&A.
Sure. Okay,
Over to you, Dr. Narayanan.
Can you hear me? Thank you. Can you hear me? Just checking.
Yes, yes.
Okay. So first, thanks for the invitation to Professor Raj Srinivasan and Professor Ravindran, and I wish the best for the Dart Lab. Let me try to share. Okay, can you see it?
Yep.
Okay. So today I'm going to talk about a little bit of my work on decision making. I mean, compared to the last talk, this is a bit different. So let me say something. I'm a cognitive scientist, so I'm really interested in how humans make decisions. That's essentially what my interest is. And so, as cognitive scientists, we study what are the mechanisms or the processes that are involved in us making various kinds of decisions. And today I'm going to focus on three factors that we have studied and we think are important, and it influences some aspects of decision making. Before I go to my work, I just want to say a little bit about something that's actually very famous. In fact, this particular book is very popular. This is by Daniel Kahneman, Thinking Fast and Slow, and any framework that is used throughout the book, and it's very important, is the notion of two systems that are involved in decision making. As the title of the book shows, obviously one is a very fast system, so-called system one, that presumably operates fairly automatically. It's very fast. You don't need to make any effort. It's kind of outside of your voluntary control and so on. Okay. And system two is this slower, attentional, effortful system that we use to deliberate. And it's slow, it is associated with volition, agency, and so on. So this notion that there are two systems and they operate differently. And of course, the decisions that we take in general is a combination of the two systems. So now the question one can ask, I mean, many questions can be asked. One question that has been asked is, if you have to take a decision, and let us say if you have to use one system more than the other, then the question is, which system is better, right? So this question has been asked before in the old classical way of asking. The usual kind of dichotomy is one system is emotional and one system is rational. And people ask, okay, which one should you use to take various kinds of decisions that we take in our lives, from simple mundane decisions to fairly complex decisions like, career, this, that, and so on. So a lot of people, of course, if you go back and read old literature or books, people will say, well, we should think very hard, deliberate, and take a very careful decision. Some, of course, may say that, no, actually, your intuition, which is something, not part of your deliberation. So use your intuition and take a quick decision. And it goes by various kinds of proverbs we have, including, for example, first sight, including love at first sight, for example. So the question is, what should we do? Should we trust our intuitive system, or should we trust our deliberative system? Recently, people started looking at this in multiple ways, and this is just one example of it. Dijksterhuis et al. And colleagues published a paper in Science in 2006, where they actually gave a multi-attribute decision-making problem to the participants, where certain things were defined in terms of 4 attributes or 12 attributes, say cars is one example. And then they asked people to take a decision in 2 conditions. One condition in which supposedly they used their attention, they deliberated about these attributes, what is present, what is not present, and so on, and then took a decision. Whereas in the deliberation without attention condition, for say 3 minutes or so, people were asked to do something else for 3 minutes, and then they come back, and then people are asked. So initially information is given, then they are given a distracting task, do something else for 3 minutes, and then they now come back and they are asked to take a decision. They are also they're asked about their attitudes and so on and so forth. And the basic finding is essentially what you see in these graphs here. When the number of attributes were smaller in number, 4, they made the better choice when they deliberated. But in contrast, and surprising to me, when there were 12 attributes, more attributes to be taken into account to take a particular decision, then presumably the unconscious or the intuitive system, that ended up, people who did that, essentially they did not think about it, they did something else, came back and then took a decision. That seemed to be better. So in fact, they called it deliberation without attention effect, and said if you are even concluded, or at least there were newspaper reports, that if you have to take a very complex decision, it's better not to think about it. You just use your intuition to do a very quick decision, right? And in fact, this particular thing, deciding quickly versus deliberating, is a commonly used manipulation to study the so-called 2 systems approach to decision. This particular effect has now history now. There have been failed replications of this effect. But in terms of our own work, we started looking at this whole notion of intuitive system, or what they called unconscious thought. And there are two core assumptions about this so-called unconscious thought theory. One is this system is supposed to have kind of unlimited capacity. It's not capacity limited, or it's not affected by attention. That's another way to say it. And presumably, whatever weighting of attributes is done to eventually arrive at a decision is optimal in some sense. We proposed, this is my student, Dr. Sumita Mukherjee, who at that point was a student, now he's an assistant professor at IIT Delhi. We proposed that this doesn't gel with what we think, that people probably don't have anything like unlimited capacity, and a simple subsampling heuristic, that is focusing on a very small number of attributes, is sufficient to produce data that would fit with, essentially fit with behavioral data. So our issue was, since we study attention, that this is the part that we don't agree with, or it's not acceptable. So we looked at it by using very, very simplistic or simple algorithms, really. And essentially, we took data from, we took a couple of data sets, but this is a data set which they gave about cars. There are 4 cars, Hasdun, Kaiwa, or whatever. There are 12 attributes, and they simply said whether this particular attribute is present in that car or absent in that car. That's it, pretty simple information. So what we did is we did 4 types of very simple algorithms, nothing complex like machine learning or anything. One is essentially we sampled these, out of these 12 attributes, 1 attribute or 2 attributes at a time, or 3 or 4, which is in the x-axis, the number of attributes. We either randomly sample these attributes, arbitrarily pick 3, or there is information about which attributes are more important or less important according to human subjects. We use that to do weighted sampling. That is, we either did random or some kind of weighted sampling. And we combined this information. We simply calculated how many features or attributes are present or absent, which is one possibility. Or even in combining them, we can just simply do a weighted combination, a linear weighted combination of these attributes. But it doesn't matter which one we used, all 4 of them, as you can see, by the time you get to 3 attributes, the car that is supposedly optimally better essentially was picked by more number of times. I mean, we ran this simulation thousands of times, and majority of the times, even with 3 attributes, across even these minor variations in the algorithm. Let me just show you behavioral data and see how our simulation results match. At the top in the table is what you see of the behavioral results from 3 different experiments. We use the same problem, the 4-car problem. And you can see that the Hackstone is picked by majority of the participants. But if you look at simulation results, even 3 attributes that are randomly picked out of the 12, and then you combine information from them, essentially that result fits with behavioral data. So there is no need to postulate that somehow intuitively people take care of all the information, in this case all 12 attributes, and somehow optimally combine them. That doesn't even to fit with the behavioral data, this assumption is not even needed. So we essentially argue simply subsampling. Most of the time, humans use certain simple heuristics, and just in this particular example, subsampling can lead to decently correct choices, even though information about 12 attributes are present. Just looking at 3 attributes is sufficient to explain the behavioral data. And there is no need to postulate something like infinite or very large capacity unconscious or intuitive thinking or whatever. So And whatever you may call unconscious or conscious thought or intuitive or deliberative thought or whatever terminologies you may use, you probably focus on a small set of attributes to arrive at a fairly decent, satisfying decision. So basically, our argument is that these kinds of paradigms and tasks conflict, notions about attention and consciousness, and this particular paradigm may not even be even assuming there is some intuitive or unconscious thought to measure this particular aspect. I mean, basically, we have also done follow-up experiments on other kinds of things, with us simply arguing that in most of the cases where people think that you need to postulate two kinds of system, contrary to what Professor Daniel Kahneman has shown or has argued for, that it may not be needed, at least in most cases, to propose. So we are very skeptical of this notion of two systems, even though I know it's very popular and there are a lot of people who use it, and it's actually a fairly popular idea among people actually. Then we move on. The other kinds of things we have looked at is to look at the effects of magnitude, and we have looked at it in a couple of different ways, in a couple of domains. I have done this along with Sumit, and let me quickly go back. One common phenomenon that has been studied in the context of prospect theory, for example, by Kahneman and Tversky, is a well-known notion of loss aversion. So, of course, here you see the typical function that you see in prospect theory. Basically, the thing is that if you compare equal amounts of gains and losses and see which has more value or which affects you more, the general idea is that losses affect you more than gains. And this, of course, is known as loss aversion. And this is a quote from a paper by McGraw et al. In 2010. This particular asymmetry in terms of losses and gains, they say the asymmetry is commonly thought to occur because people expect the pain of losing something to exceed the pleasure of gaining it. So, interestingly enough, in the literature, this is actually a behavioral finding, but sometimes people use it as a mechanism or even an explanation for certain things that people do or do not do. However, this has been contested as well in many ways, and I'm going to focus on only one particular aspect here, and that is magnitude. So there was a study by Harnick and colleagues in 2007. They asked two groups to rate small magnitude gains and losses, and then they found, using a bipolar scale, that is a scale that goes from a negative number to a positive number, and they showed that gains are valued or were given a much higher value than losses. Now, McGraw et al., coming back with and talking about this result, argued that actually speaking, you get these deviations from loss aversion predictions because of the nature of measurement method used. That because this is what we normally in psychology or behavioral economics would call a bipolar scale. It's actually, if you use a relative scale or a single, simply a scale that goes from 0 to, say, some maximum, then you will not get this result. And that's what they argued in their 2010 paper. Okay, so in 2017, I mean, we did this study, me and Sumit and a couple of other colleagues. We did 4 experiments, and we used 2 kinds of paradigms. One is the typical gambling type scenario, where you have to make a choice between 2 gambles, and you may gain or lose. And in the other case, where we fixed a reference price for some particular product, and then we talked about either increase in price which is like a loss, and a decrease in price, which is like a gain. Taking the arguments by McGraw and colleagues, we used unipolar scales, essentially a scale that goes from say 1 to 5 or some positive integers or numbers, or a relative intensity scale. I will tell you what a relative intensity scale is. And since they argued this is the best method to capture loss aversion, we used essentially what they recommend. And you can see this is from experiment 1. This is presented in one particular way. On the y-axis, you have intensity of feelings, averaged, which of course can go from 1 to 5. On the x-axis, you have the magnitudes. That is, you can have like gains of 5 rupees versus loss of 5 rupees. Here it would be gain of 500 rupees versus loss of 500 rupees. And essentially what we found is that small magnitudes, gains, actually they're valued more. The feelings of emotional feeling that they express, they thought they would have if they gained 5 rupees was more than losing 5 rupees. So for small magnitudes, it's actually the other way around. Not only we do not have loss aversion, we actually have a bit of a gain preference. Of course, as the magnitude increases, in this case, these are done with students with small amounts for purposely, because they don't handle very large amounts in their life too much. By 500 rupees, you start seeing hints of loss aversion. At 500 rupees, or maybe in this experiment at 500, or sometimes at 250. If we convert this unipolar scale, 1 to 5, to a relative intensity scale. So take when they said gain is valuable or will produce a more intense feeling than loss, which is gain greater than loss, or gain is equal to loss, the ratings are same, or gain is less than loss. Just convert this into a 3 kind of categorical scale, a relative intensity scale, and then replot the data. Again, you see, of course, a lot of times because these magnitudes are small, they are actually saying it doesn't really matter, gain or loss, which is expected by them. But what is important to see is how many percentage of participants they say gain is greater than loss, which is say here 30%, and here it's 5 to 10%. Now you can see it reverses at 500 rupees. So essentially what we showed is that for small magnitudes, we do not have loss aversion. In fact, we may have gain preference. And at large magnitudes, maybe McGraw and Daniel Kahneman and other colleagues are right, that you actually get loss aversion. But the phenomena as loss aversion is magnitude dependent. It is not something that's universal across all possibilities. We also did three other experiments. Data from a couple of other experiments are shown here, but essentially all of them show the same pattern. Again, in this case, we directly gave a relative intensity scale to participants. Again, you see the same pattern. Now, when you give a relative intensity scale, you can see that as the magnitude increases, the gain equal to loss proportions go down, which is expected. But what you see is here there is no loss aversion, gain greater than loss, there are more participants than gain less than loss. And by the time we get to 500, it reverses. You see typical loss aversion. This is, of course, typical gambling type questions, right, in terms of choices. A more realistic one is to look at something like price changes. People say some price and then suddenly you go, there are discounts. Or sometimes prices increase. It happens online or it happens in a shop as well. So when we phrase it in terms of price changes and then looked at manipulated magnitudes, again we get a similar result. There is maybe a bit of not so big gain preference or definitely no loss aversion at small magnitudes. But you start seeing actually you don't even see any loss aversion even at 500 in this particular experiment. So Literally, loss aversion was not present in this particular experiment when we use price changes rather than a gambling type scenario, which is fairly common in behavioral economics or decision making literature. What we have done more recently is to change the domains and then see what happens. So one of the things we are always interested in is time. We always make calculations about time. Right now, I'm thinking hopefully I will finish my talk in 40 minutes. We stand in queues evaluating time. We travel and we look at time. Sometimes we lose time. Sometimes we are early. Sometimes we are late. So the question is that whether the kind of decisions we take with respect to time into consideration, and we do that fairly commonly in our life, whether we see these phenomena like loss aversion and risk aversion with time as well. The answer generally is kind of yes, to some extent, although the results have been somewhat mixed. But we essentially looked at the same kind of magnitude effects with time. So in this particular experiment, essentially the problem is posed in terms of two queues, and then people are you can have gain or loss of time because one queue moves fast or one queue moves slow or could move slow, and then we looked at various magnitudes of gains. And of course, all these options were shown to the same subject, and the order was randomized across participants. So this is what we call a within subject design, same subject doing. And on the y-axis, again, you have percentage of participants. On the x-axis, you have time in minutes. And you get the same effect again, which we saw with money earlier. The small magnitudes of time, people actually say that gain, which is in black bars now, has a much larger effect than loss. So we actually see a gain preference at small magnitudes when we are taking decisions about time. At larger magnitudes, say for us, a queue, 2.5 hours is very long. Again, a loss of 2.5 hours. That's happened in India. And here you see that you have loss aversion. So more participants feel that there will be more effect of loss than gain. But interestingly, while we do see loss aversion at larger magnitudes, we do not see it. We see the opposite with smaller magnitudes. Now, it's not simply the case that, again, to see whether the effect would generalize, we also looked at other domains in which we make decisions about time. So these two on the right are examples of results from essentially a travel type scenario where you are traveling and then either from, in this case, just to travel without saying anything about purpose. And again, what you see is that there is gain preference at small magnitudes and not even loss preference at these magnitudes. Of course, we gave a reference point. I think it was 45 minutes to take time to travel wherever you are going to and fro in this particular example. We changed the scenario where people are going from work to home versus home to work with the general notion if you're traveling from home to work, it's more important for you to reach on time. There is much more pressure on you versus it's much more consequential. Whereas if you're going from work to home, it's generally less consequential. And this is what you see there. As you see there, now the effect is dependent, well, it is dependent on magnitude as well, but it is also dependent on whether you are going from home to work or work to home. So loss aversion is more if you are going to work and less if you're going back home, okay? And of course, if the magnitude increases, the loss aversion magnitude increases even more. So you do get loss aversion results with time. So this effect with money generalizes to some extent. But it's also the case, it's still dependent on magnitude, and it changes as a function of magnitude, and it also changes a function of consequence. We have also looked at risk aversion with respect to time. Essentially, we used some kind of a travel app scenario, which is it's like a bit of like a Google map. Two routes are shown. The two options are shown at the bottom here. We did two experiments. One experiment in which it says if you take this route, which is 1.2 kilometers, it takes 5 minutes or whatever number of minutes. In another case, it takes, of course, more or less. And then people are supposed to pick either the sure option or the risky option. And then we can see, depending on the proportion of time people choose the sure option versus the risky option, whether there is risk aversion or not. And we also manipulated the magnitude of the time, since we know magnitude influences risk aversion anyway, from 10 minutes to 180 minutes, okay? And the risky option, I mean the magnitude, the proportion essentially changes in terms of small changes. So for example, let's take an example, 180 minutes, it can be 150 or 210, or it can be 90 or 270. Even though the mean is the same here, the two endpoints of the range are different. There is more variance here and less variance here. We also changed the terminology, words in terms of R. In experiment 1, we use R. In experiment 2, we use 2. The simple logic being R means it's binary, either this or that. 2 means it could be any time between this range of interval that is specified here. What do you find? Well, again, we do find risk aversion for larger magnitudes, especially when we use R. As you can see here, people go for the surer option more than the risky option for 180 minutes. We just plotted the two endpoints here just to make the point. We actually did a logistic regression, and essentially the results show that magnitude has influences risk aversion. The percentage of change did not matter much, or at least it wasn't significant here. Then we changed simply the word R to 2, which essentially means the whole possible range of times are possible. Of course, the mean is still the same. So here what happens? Now here what happens is that you have both an effect of magnitude and also an effect of how much change there is. But you do get risk aversion with time. Okay, let me see how much I have. I have 5 minutes. Okay, so this is the last one. Yeah, sorry. Do I have 5 minutes?
Yes, Prof.
Okay. So we are going to look at, we looked at control, and we have done it in multiple ways. I'm going to present a very simple experiment here. We are doing a much more realistic game type study, which actually shows similar results, but I'm not going to present it because it's not fully completed yet. Essentially, the basic idea of temporal discounting is something that I'm sure all of you are familiar with, that if I ask you to make a choice between a small immediate reward versus a delayed but larger reward, people a lot of times go for the smaller immediate reward. You will say they are not patient. This is called impulsivity, and this is something that can be measured in participants using something called a discount rate K. Essentially using a fairly simple formula, which is B, which is the small reward, A is the large reward, D is the delay. This is, and people have argued that this discounting is hyperbolic. We're not going into the actual discounting function, which is better or worse here. But here our interest is slightly different. One way to do it in the lab is to use essentially a questionnaire, 27 items, 27 choices actually, which has been used by Kirby and colleagues, which picks a small immediate reward with a large delayed reward. the three levels of reward magnitude, small, medium, and large. I will show you an example in the next slide. What we did is one important issue to understand control is to look at variance. I mean, the more variance you have in a system, things vary a lot, it becomes much more difficult to control. Okay, so just using that intuition, nothing more than that, we manipulated levels of variance in experiment 1, 2 levels, and experiment 3, 3 levels. So this is essentially what we used. All you need is to simply read one row. The presentation order is randomized. This is just one example here. So just to understand this, this essentially asks if you want to have 578 rupees today, or you just now are given a range of rupees, 560 to 630 rupees after a certain number of days. In fact, in this example, it's 186 days. The mean, by the way, is fixed and something that is controlled for. But what we manipulate is the variance. So at both levels of variance, the means, the expected values are the same. We measured this parameter k, and this is, of course, calculated and shown here on the last column. Okay. Of course, we do this experiment with participants, and we measure this parameter k, and what do you get? Well, in experiment 1, there are 3 levels of magnitudes, different ranges of rupees. They had originally done it dollars, which is converted into rupees. Purchase parity. Yes. Hello. Who's there? Okay. And essentially, with small, medium, and large magnitudes, we did not get any effect of variance, but with small magnitudes, we did get an effect of variance. That is, the k value was larger when the variance increased. That is, to put it simply, that when there was more variance, then people became more impulsive. When we increase the number of variance levels, now we have 3 levels of variance, we added one more, and of course this we could do only with large magnitudes, and we repeated the experiment. Now we get an effect of variance even with large magnitude, essentially, showing that k value is larger here significantly compared to this. So the basic conclusion here is that as the variance, as the system in which you live, so to speak, has a lot of variance or noise, things are changing rapidly, then people become more impulsive. They go for an immediate reward in this particular case, and we think it's a common mechanism that people use and can explain certain other results that people have used to study various kinds of things, including decisions made by poor people and so on. So to conclude, the notion of two systems is fairly popular in decision-making literature, but we would like to argue that it's not necessary to propose two systems, especially one powerful, intuitive, unconscious system to explain decision-making. And it's very important to study different factors to explain how we make decisions. Thank you. Now I'm free to answer questions. Sorry, I probably exceeded my time.
No problem, Prof. Thank you so much. It was a very insightful talk on largely loss or risk aversion. Let's see if we have any reactions or questions. I do not see anything in the
question.
Professor Raj, yeah.
Yes. So, Professor Narayanan, thank you very much for a very interesting talk. I had really two slightly different questions. One was this idea of mean variance optimization, which seems to be kind of widely used in certain domains, particularly finance. Do you see any analog to that at all? Because I think in this,
I don't know. I mean, I guess it could, but See, part of the problem is I'm not sure with real decision-making experiments that people make where we control for multiple factors. I can see the analogy, but I don't know whether I can surely say that they are very similar. But it would be interesting to check it out.
Right. And then the second part of my question was, so if you think of a decision-making algorithm like the classifiers or other tools that the previous speakers talked about, if the accuracy of that is the quantity which is variable, meaning on certain occasions it's perfect, whereas in other occasions it's totally, off. Would this idea of loss aversion apply to that context as well?
I have no idea. In fact, I do not know whether. See, part of the problem is that the loss aversion is about assuming it's when it's there, is about the kind of emotional feelings we have, right? About losses that we don't want to lose too much because it has certain kinds of implications for us. Now, unless the machine learning algorithm brings in factors like affective or emotional consequences, which they normally don't do, because most machine learning algorithms, if it is supervised, simply going to say, well, these are the two decisions, two classes, and there's no explicit representation of affective consequences at all in most machine learning algorithms, or at least that one I know, the ones, at least the standard ones.
Sure.
I know there are some people who try to do certain things in affective computing and all that. In generally speaking, because loss aversion is really related to emotions, and unless we start bringing in the presentations of emotions or emotional feelings explicitly into these algorithms, I'm not sure how they are going to show it. I mean, I guess one can cook it up in some sense explicitly, but whether it will arise as a natural consequence of decision making is something I'm not sure. I'm not optimistic at this point, but I may be wrong. I don't do machine learning.
Okay. Sure.
Maybe others who are experts on machine learning can say something about that.
Sure, that's a fair point.
Anybody else? All right. If others don't have, I have a couple of questions, Dr. Narayanan.
Sure, please go ahead.
Yeah. How would you address the questions on reductionism, on how we model some of these things? As you rightly said, we don't really model effect, and somehow we can do that, if not accurately at least. How do you address the allegations of reductionism on our approaches?
That's a philosophical question. Well, I mean, it depends on what you mean by the word reductionism, right? In science, the word reductionism is used in certain different ways. For those of you familiar with how the word is used, right? If reductionism in that sense can happen, it's been a philosophical question which is more than thousands of years old, and the answer remains open. We do not know yet. I mean, we keep debating about this. The general idea of doing science, at least in some aspects of science, where reductionism has been reasonably successful. Okay, I won't say fully successful, but reasonably successful. Like, for example, physics or chemistry, where you can try to reduce what you see as a macro property to as arising out of interactions between certain properties at the micro level. Even there, it is just simply not possible. As somebody has pointed out, why people keep saying that everything, for example, is based on quantum mechanics, I don't think anybody is ever going to write all the equations to show how a car runs using all the elementary particles in a car. It's just a belief in principle that it's possible, but I don't think anybody is practically ever going to do it, and no computer is
Very
ever
true.
going to run that simulation. So the issue is
Very true.
we believe what normally happens even in those cases is that there the scale is in terms of size, right? So usually speaking, you have smaller particles, let us say, and you're trying to explain, say, electrons or protons, and you're trying to explain something at the atomic level or something at the molecular level, or maybe a bit larger than that. Usually there, of course, it's successful, right? So reductionism works there. Even there are issues which I will not say anything about right now, but at least that's where we can see that.
Yeah.
So the
In
issue
human
of,
processes.
so in principle, what normally as scientists we can do, and we do that, is to see whether something works or not. Ultimately, it has to be tried. So if I am a reductionist, then all I can do is apply the techniques of reductionism that I have, and then see how far I can go. What are the limits of knowledge that I can reach? So I would not be too pessimistic as well and say we should not try reductionism, because eventually things may not reduce at all. That also doesn't make too much sense in a pragmatically. So the way we look at limits of knowledge is to see whether we can theorize. We try different approaches and see how far we can go, and establish the limits of whatever knowledge we have in whatever domain of science that we are looking at. In my case, it's of course the study of mind, since I am a cognitive scientist. We have a very long way to go. So this is something we keep debating a lot, both in classes and amongst us, for hours and hours without any answer. So unfortunately, I can't give you an answer.
Yeah, it's very difficult to conclude. It was more in terms of human processes, because we have more than 400 different fallacies and biases to work with, not just the loss aversion, especially in social scenarios of altruism, pro-social behavior, where we are willing to take and accept loss.
Yes.
So in that context, I think we are well past time. So thank you so much. I do not have further questions from the audience. Thank you so much, Professor Narayanan. Over to you, Raj.
Thanks a lot for patiently listening to this discussion.
Thank you, Professor Narayanan, and thank you, Lata, for chairing the session. Now, let me turn over the last session, which is basically a wrap-up of everything we have discussed over the last 4 talks, including the 3 today and the 1 yesterday. To do the wrap-up, I invite Professor Babji Srinivasan, who is with the Department of Applied Mechanics. Babji, over to you.
Yeah, thank you, Raj. So first of all, I would like to thank all the speakers for delivering wonderful lectures. And in a sense, broadly, all the speakers were talking about the interplay between interplay of human factors and inherent risks arising from workplaces, if I have to put it in a broad context. And I think that specifically the goal of or one of the overarching goal of DART lab to address those issues, which issues such as risks coming out of interplay. And starting from the yesterday's speaker, Professor Jamieson, who gave an idea about overview about all the verticals, I would say, starting from aviation, process industries, how this trust, the relation between trust and automation. And that was a talk kind of set up a place where we see the domain where all this kind of problems arise. And that was followed well with today's first speaker, Kastikopoulos, who talked about the models, the critical aspect, following up right after the problem setting, the models which are definitely needed to solve this kind of problems. So I see that there is a bottom up and the top down approaches, where there are simplistic models and then fine grained models which are specific to domain. And that was a wonderful talk giving about an overview of the modeling part. And then it was followed by Dr. Manish, who was giving use cases, which actually is precisely a requirement at that stage to see where all these models in this broad area, how does it span out. And that's where the talk by Dr. Manish comes out and explained how this across the domains, especially in the use cases in finance domain, applies. And finally, the interesting talk by Professor Narayanan, asking about fundamental questions that are challenging questions that are a part of this, usually the hidden part of this, the entire build up. So that was also wonderful, which tries to close all the, starting from the bottom up, top, all the domains, and finally to narrow it down to these, minute, or the scientific questions, challenging questions. And it was well in our line with our, the dot lab goals, where we are trying to address, this interplay challenges between human factors and risks in all verticals, in most of the verticals. And I again thank the speakers to for giving such lectures. And yeah, thank you everyone. Over to you, Raj.
Okay, so that brings to a close the inaugural lectures, but I certainly hope that this is only the beginning of a long series of interactions you will have with all the speakers, but also with industry and other, with the government and so on. So with that,
Raj,
thank you all.
just to add one more thing,
Yes, Nandan, go ahead.
we have two speakers. Perhaps just a note on how we are actually looking to kind of create a community that of external people in other universities, international as well as national, who will continue to be affiliated with DART in a more formal capacity. Perhaps just a word on that.
Yes, thanks for the reminder, Nandan. So I think it's like I mentioned in the opening remarks yesterday evening, the idea that we need to incorporate human behavior into all considerations, especially when you talk about risk, kind of defines itself as something that no one discipline has ownership of. We need to look at it from a technology point of view. We need to look at it from the domains point of view. We need to look at it from the human, which again is inherently very complex. And so clearly, even though IIT Madras has interests in this, we don't think we have all the expertise required. We also think modern day science and technology is done with large groups, all of us bringing our own strengths and fortes to bear on interesting problems and working together to develop something big. So that's kind of the founding philosophy of the Dart Lab. And so we really expect to reach out to you and to work with all of us here and others to try to push the envelope by incorporating points, various strengths, various capabilities. So I hope all of you would be receptive to this suggestion of working in tandem, working together collaboratively. Obviously, there are those little details that we as academics are aware of, like funding and students and so on. But increasingly in this day and age, I think it's easier to tackle those than the science. Perhaps the science is where the real challenge is. And so I think it will be fun to do it all together. So with that, let me wrap up. Nandan, was there anything else you wanted to add to that?
No, not at all. I think it's perfect.
Okay, so if not, let me bring this session to a formal close, and certainly stay back and we can have a more informal discussion once we go off the public live session. So thank you all.
Thanks a lot.
Good.
Thanks a lot.
Thank you. Thank you. Bye-bye.
Bye.
Mr. Kannan, can we disconnect the public portion? Mr. Kannan, can you hear me?
Yes, sir. Namaskar, sir. I was actually in another live conference. I just came.
Excellent.
Yes.
If we can disconnect from the YouTube now.
Yeah. Thank you so much, sir. Yes, sir. It's done.
Thank you. So I think we have